Hello, I'm Ann Pope. I'm an environmental engineer and I work on preparation and modeling files for risk assessment. I've worked for EPA for 27 years on inventory development and on risk assessment modeling. This module covers sources of toxic air pollution in the risk assessment course. There are a variety of anthropogenic or man-made sources of outdoor air. These sources include mobile sources. Mobile sources include on-road sources such as trucks, cars, buses, as well as non-road sources which include airplanes, trains, commercial marine vessels, and non-road equipment such as construction equipment or farming equipment. It also includes stationary sources. Stationary sources include factories. It also includes our homes. If we have wood stoves, it includes farming sources from ag tilling, as well as other sources such as dry cleaners or gasoline stations. Okay, let's look at the slide that was introduced in the first module on the risk assessment process. If you look in under exposure assessment, you will see the source identification block represented by a factory with air pollution coming out. You will notice that the source identification block is the first block that feeds into the risk assessment process. So in my mind, this is the most important block because we have to have good data coming into the risk assessment process. The risk assessment results, or the characterization results, are going to only be as good as the data that we feed into the model. So it's very important that the source identification information is accurate and correct. Let's talk a little bit about the different types of sources of outdoor air toxics. We divide our ambient emission sources into 4 groups at EPA. Major sources and area sources are stationary sources. On-road and non-road are mobile sources. So if we look at the pie chart from the 2005 National Air Toxics Assessment, you will see that the area sources and other sources, including fires, accounted for 36%, are the largest majority of our current anthropogenic or man-made emissions. Our major sources, which primarily come from plants and facilities, only account for 19%. And our mobile sources, on-road accounts still for 26% and non-road for 19%. So the total, the mobile sources account for approximately 45% of our ambient air emissions, and our stationary sources account for 55%. Let's talk a little bit more in detail about the different types of sources. What are major sources? These are stationary sources that release greater than 10 tons of a single HAP per year, or hazardous air pollutant, or 25 tons per year of a combination of hazardous air pollutants or air toxics. The emissions are usually released from facilities. They can be released from a variety of different units within facilities. They may be released as fugitive sources from equipment leaks. They might be released when we're conducting material handling, loading, unloading, or they can be released from stacks or vents from processes. We have 174 major source categories that we have developed regulations for. Area sources are stationary sources that emit less than 10 tons per year of a single air toxic or less than 25 tons per year of a combination of air toxics or hazardous air pollutants. In general, area sources are usually smaller facilities or aggregated sources. They include such things as gasoline stations, dry cleaners, car painting shops, chrome electroplaters, and at residences they can include backyard burning barrels, residential wood burning, which includes wood stoves and fireplaces. EPA has listed 70 area source categories that we've developed regulations for to date. Mobile sources include both on-road and non-road mobile sources. Most of our mobile sources regulations have focused on on-road cars, trucks, and their fuels. Non-road engines and other non-road sources are also significant sources of air toxics, and we have regulated these sources as well. The main types of non-road sources that we have regulated, the main type of pollutants that we've regulated include diesel particulate matter, and we have regulated 20 volatile organic compounds and metal HAPs, or air toxics. Another source of ambient air toxics are natural sources, and these are not regulated. These are naturally occurring sources, and they include such things as forest fires, volcanoes, entrainment of dust, so it would be wind-blown dust coming back up into the atmosphere, cycling of mercury, which includes a resuspension of mercury from water bodies, and then atmospheric production of formaldehyde and other chemicals that occurs from other pollutants that are released, such as volatile organic compounds. There are other types of sources as well of ambient air toxics pollution. These are not traditionally included in our risk assessments. They include accidental releases such as explosions at factories, long-range transport of global pollutants such as mercury, and then we have persistent pollutants that just hang around in the atmosphere like carbon tetrachloride. Carbon tetrachloride emissions have decreased significantly since the passage of the Clean Air Act, but our monitors still show just a cloud that's up in the atmosphere. These are persistent because they have very long half-lives. And then re-entrained pollutants that we discussed earlier, such as wind-blown dust. Indoor air sources we will not be focusing on today, but the indoor air can have higher concentrations of air toxics than our outdoor air. The outdoor air pollution comes inside. We spend more than 80% of our time indoors, the average American. So we have more exposure coming in from indoor sources. Other sources within your homes or in your offices are chemical supplies that we use for cleaning our homes, or pesticides. We also have glues and solvents and other aerosols. Our heating and our cooking are other sources of air toxics within our homes. And then the different types of materials within our homes release air toxics, such as plywood, such as countertops, such as mothballs, such as our dry cleaning bags and carpeting. EPA does not currently regulate sources of indoor air. Okay, so we've talked a little bit about the sources. Now we're going to talk about how do we quantify our emissions. So as part of the source assessment that we were looking at for the risk assessment, we have to come up with estimates of air toxics to be modeled. Okay, so we're going to talk now about how we estimate our emissions for stationary source categories that feed into the risk assessment. We model two types of stationary sources, point sources and non-point sources. Our point sources include major and area sources. We prefer these for risk assessments because we get better results in our risk assessments. So we want to know the specific units that are emitting the emissions within the point source, and we want to know the specific emission release point, as well as the characteristics. The point sources include both major and area sources as we defined air toxics. Non-point sources are aggregated sources, and we only include area sources in these estimates, as well as fires. The non-point sources are aggregated at a geographic level. They might be aggregated at a county level, at a tribe level, or we can use shape files to identify the geographic area. So this would be, in this example of dry cleaners, it may be that you have a county level estimate for all the dry cleaners in your area, or you could choose to estimate emissions of each individual dry cleaner and include those in a point source estimate. So what do we need to consider for point sources? First of all, we have to know, is the source a major or an area source for regulatory purposes? And then the level of detail that we need information about the facility. What is its name? Where is it located? We need information at the unit level. So what is the specific unit? What type of unit is releasing the emissions? And at the process level, an emission release point. The emission release point can either be a stack or a fugitive release. What other information do we need to know for our modeling? We need to know the specific latitude and longitude of each release point. It's not good enough just to give us a facility latitude or longitude, and we need that to the 5th decimal place. We need stack parameter information, so we need to know stack height, diameter, exit gas temperature, velocity, and flow rate. If it is a fugitive release, we need to know the area of the fugitive release. We need to know the length, the width, and the angle. We need information on control devices. And then we need emissions by pollutants. And for air toxics, it's very important that we use individual CAS numbers, chemical abstract service numbers, to identify the pollutant, because each individual pollutant has different risk or toxicity information for cancer and non-cancer effects. We need to know the operation schedule for the plant. We need to know, is it running 7 days a week, 24 hours a day? Is it running 2 shifts, 5 days a week, 1 shift, 5 days a week, or 1 shift, 7 days a week? We need to know information about the process, and for this, in our inventory data, we use what are called SCCs. These are source classification codes, and they are specific to air pollution sources. They describe the specific process to tell us, for instance, the type of storage tank that it is, or the specific stack release type, etc. And we also need to know about the facility, and for these we use the NAICS code. For non-point sources, these are sometimes in our criteria air pollutant inventories called area sources. This definition is totally different than the definition for air toxics. Non-point sources include smaller point sources grouped by source category, such as gasoline stations or dry cleaners. And then they include other area sources such as forest fires, leaf burning, residential wood combustion, etc. What do we need to consider when we're developing inventories for non-point sources? First of all, in our inventories, we have to make sure that we are not double counting emissions with our point sources. So you have to make the decision, am I going to include that service station or dry cleaner or electroplater in a point source inventory or a non-point source inventory? For wildfires and prescribed burns, the current methodology is to estimate the emissions as hourly events with lat longs, and this allows us to model those specific events. So what happens in the inventory? They move hourly, and we look at the burn characteristics. The detail that we need, first of all, we need the geographic area or county or a shapefile. It would be better if you're going to inventory sources for risk assessment to use shape files, because we can get at much smaller geographic areas where the emissions are actually occurring. If you do not provide shape files, then you will need to provide an allocation method where we can take a county level emission estimate and allocate it to the specific census blocks for risk assessment modeling. We also need source classification codes to identify the type of air pollution process. We need NAICS codes if they're used for industrial processes. And again, we need the emissions that are reported by pollutants with the chemical abstract service numbers. So we've talked now about stationary source emissions. Let's discuss mobile sources. For mobile sources, as we've said, we have on-road sources, so these would be your vehicles that are found on highways, cars, trucks, buses, motorcycles. And we have non-road equipment. Non-road equipment are sources that are not found on roads and highways. These include things such as 2- and 4-stroke engines in our lawn mowers. They include construction vehicles. They include forklifts. They include farm machinery. And then we have another source of non-road vehicles called ALM, which is aircraft, locomotive, and commercial marine vessels. The reason I have split non-road and ALM sources is that we inventory them different. So let's look at how we inventory them. For mobile sources that are on road, we either estimate them for a geographic area, very similar to our non-point sources, usually by county or tribal area, or we can estimate them for individual roadways within a geographic area. If we estimate on-road sources at the county level, then the emissions are allocated to specific roads, usually the major highways within a county, and assigned to that in risk assessment modeling. Non-road equipment, those are usually inventoried at the county level. Some of them may be in your point source estimates. If we had trucks that are bringing in ore on a mining operation, then those may actually be in the point source inventory. But generally, non-road equipment are inventoried at the county level, and then we have to do an allocation back to individual census tracts. Airport mobile source emissions are now estimated as point sources. So for all the commercial and non-commercial airports, we inventory them as individual runway emissions for takeoffs and landings. And we have essentially a shape file, a rectangle, that shows the runways, and the emissions are assigned to the runways. Commercial marine vessels are currently inventoried as a mix of point and non-point emissions. At the port, these are usually inventoried as point sources. And then the underway emissions are estimated as non-point emissions. Locomotives or trains are also inventoried as both point and non-point sources. So a rail yard will be a specific point that we estimate emissions, and then we have essentially line emissions for the counties where the tracks run through. Now we're going to talk about how to develop the risk input modeling files. So the first thing that I would recommend that you do is you extract the data from all available sources. And then what you want to do is to look at that data that we've first extracted from the available sources, and we review the data to identify, are the data old, are they erroneous, are there missing data fields that we absolutely have to have for our modeling. After we do that evaluation, then you have to collect the data that you are missing to develop your risk modeling files. In general, we go back to facilities, we may go to trade associations, we may go to other EPA data sources, or we contact state, local, and tribal agencies for the data. So we collect our data, we receive it back into the agency, and then we prepare our draft risk modeling files and fence line maps. Fence line maps are very important for risk assessments. After we prepare the draft file, then we QA the file. If we find problems, we have to go back to the original data providers, and we have to get the data resolved. We have to get information in order to revise the file. Once we're satisfied that the files don't have any more problems, then we prepare the final modeling file and the fence line maps and send them on to the modeler. The fence line maps are usually prepared in a GIS application, ArcGIS. So if we look at this flow chart, the most important steps in the process are collecting the data that are needed and the QA. In the overall risk assessment process that we've looked at multiple times, Darcy Smith has given a presentation on planning. It is very important in your planning step that you allocate enough time to do the collection of the data and the QA. If you shortcut these two steps, you may have to remodel, and it's going to cost you more time and more resources. And in some cases, we don't have resources to remodel. So it's very important that you spend the time up front planning on how am I going to get this data, how good do the data have to be for my risk assessment, and then have a routine that you run through all the QA steps. So we QA all of the data inputs going into the modeling files. We spend quite a bit of time looking at latitude, longitude QA and looking at the stack and fugitive parameters, as well as the emissions. Are the right pollutants associated with the category that I've collected? Are they missing? Are certain processes missing? So my advice is to make sure you account for these two steps in your process, and you'll get much better risk results from the assessment. Let's talk a few minutes on how do I quantify or estimate our emissions. We have a variety of techniques. We can use continuous emission monitors or CEMs. We can use source tests. We can use material balances. Material balances should only be used where there are not chemical transformations. So by that, they're usually used for coding activities. You would not want to use them where a process has a chemical change. Emission factors and activity data are used. Fuel analysis can be used. There are various emission estimation models that are very good, such as TANKS and Water9. We can also use criteria air pollutant emissions for volatile organic compounds, or VOC, and particulate matter. And if we have what are called VOHAPs, or VOC hazardous air pollutants, or metals, we can apply speciation profiles that would give you percentages of the individual air toxic compound of the VOC or PM. And then finally, we can use engineering judgment if all else fails. Okay, let's look at this graphic in detail. And what the graphic is explaining to you is that we have cost versus reliability of the emission estimate. So you can look at the trade-off, and you have to decide how good is good for my risk assessment. If I'm basing a rule on a risk assessment like we do at EPA, I need very high quality data. If you're just trying to do a screening risk assessment to see if there might be a problem, you might want to use a less expensive emission estimation technique. So let's kind of run through these. So engineering judgment or extrapolation, that's your cheapest method, but it also has the least reliability. Usually for the extrapolation, it might be better if you had the facility estimate from a prior year that you could extrapolate, maybe based on the amount of materials that you're using, or your sales have increased or decreased. If you are extrapolating to another facility, similar facility, that wouldn't be as good. It wouldn't have the individual controls. The next method from the bottom is the emission factors and throughputs, and this should say census emission factors and throughputs. So this is where you're basing your emissions on population. So it might be if I was trying to estimate emissions from hospital sterilizers, I would look at the population of the county and develop an emission factor. It would say, based on this county's population, I'm estimating that it's going to be X amount of emissions of ethylene oxide. Material balances we talked about. While this is a cheaper or less expensive method to estimate emissions, for some source categories such as coatings, it would have a high reliability. For other categories, you should not use it. Surveying is where you send out surveys to specific facilities to gather data so that the facility is reporting their emissions back to you. The next emission factors is a process-based, so that's where you're using an emission factor from AP42 in general, and you have specific throughput data, usually production data, to base the estimate on, and these are based on source tests, the emission factors. But you have to remember with emission factors, these are average. So in theory, 50% of the emissions should be higher, 50% should be lower. So it doesn't get at the specific facility. Then we've talked about emission models such as tanks, Water 9, and then finally our CEMs and our stack testing. Those have the highest reliability. CEMs will cost the most, stack tests generally cost a little bit less. So once you've selected your emission estimation methodology, and this is going to be influenced by your data quality objectives, so how good is good? How good does my data have to be? And looking at your resources. So it's a balancing act. So once you select your emission estimation method, then we have to identify the data that we need to collect. So what kind of data do we need? Do we need source tests, direct reported emissions data? Do we need capacity design data? If we're using emission factors, we want to see the emission factors and the throughput. We also collect other data that are needed for modeling. So we need to know operational data. We need to know pollutants. We need to know the latitude, longitude, or the locational coordinates. We need to know stack parameters, fugitive parameters. We need to collect control information. We need information about the facility, so we need to know how old are the equipment. This influences, if we're using emission factors, the emissions. We need to know the raw materials that they might be using or storing. We might want to get the regulations that the facility is subject to. If we're looking at existing emissions information, EPA has two sources of anthropogenic air emissions data. That's the National Emissions Inventory and the Toxic Release Inventory. Sometimes, though, you will want to go to gather additional data from state, local, and tribal agencies, from permit files, and we have a new source of data, the Emission Reporting Tool, or ERT. Many of our air toxics regulations require that facilities submit compliance source test data to EPA. The ERT collects compliance source test information. Facilities are required to use the ERT to submit their data. Within the ERT, in addition to concentration data, there's information on coordinates or latitude, longitudes, stack parameters, fugitive parameters, and SCC codes. I strongly recommend that if you're starting out to prepare a modeling file, that you look at the ERT data to see if the facility that you're interested in is in the ERT, as well as the other sources of data such as the NEI and TRI or state and local tribal files. The National Emission Inventory contains hazardous air pollutant or air toxic and criteria air pollutant emissions. It includes all anthropogenic sources, so it includes major area mobile and some natural sources, primarily forest fires. It's updated every 3 years, so it's on a 3-year cycle, 2005, 2008, they're currently working on the 2011. It's primarily compiled from state, local, and tribal inventories. It then includes other data from EPA that's filled in, particularly for mobile sources and non-point sources. The NEI is a modeling inventory. However, state, local, and tribal agencies are only required to report their criteria air pollutant emissions to the NEI. Hazardous air pollutant emissions are not required by EPA. The Toxic Release Inventory provides emission estimates of 650 chemicals across all media, air, water, and land. TRI emissions are reported at the facility level. For air releases, they are aggregated as a single fugitive release and as a single stack release. The data is very easy to access. It's updated annually. You can identify sources in your study area, but the TRI is not a modeling inventory. It does not include individual units, processes, stack parameters, fugitive parameters. Other data sources, we talked about the ERT already, but we can look at permit files, and most of these are online, so you can go to individual state air pollution agencies and download permits for the specific facility. In some cases, we have regulatory modeling data, so for a number of source categories in our residual risk and technology program, we have already developed regulatory modeling files that you can access. These have gone through review during the rule development process, and they often have much more refined data and oftentimes more recent data than the NEI. You could also contact individual facilities to request specific information. And you can also go out with survey data if you were looking at non-point sources. So you could do surveys of the number of homes in an area that have wood stoves and the type of wood stoves that they have. You can look at service stations in your area and get information on whether you're using stage 1, stage 2 controls through survey data. Now we're going to discuss what data fields do we need to include in our modeling file. And we're going to focus on point sources because you get better results if we model point sources rather than non-point sources in our risk assessment. So what information do I need? One thing that I should note, you should extract information on all pollutants from your various data sources. So you should include your hazardous air pollutants, your criteria air pollutants, GHGs, and non-regulated pollutants that you might want to model to get risk results. So the first thing that we need is facility information. This information includes facility IDs. We need state facility IDs. We need Federal Registry System IDs that EPA maintains for all facilities, or FRS IDs. We need NEI IDs, TRI IDs. If you have AFS IDs from permitting files, we need to include those. You need the name of the facility. You might want to include the parent company with the name. We need the physical address of the facility. We need to know what state, county, tribe the facility is located in. We need to know information about the facility, so we would like to gather the NAICS or the SIC code. We need to know whether the facility is a major or an area source, and we need to know the operating status of the facility. Is it open? Is it temporarily closed? Is it permanently closed? If so, you probably would not want to model it. Then we need information about the regulatory categories. So in the NEI, we would pull out the NEI regulatory code. We want to know if it's subject to a MAC standard or an area source standard. We also need information about the compliance and permits. So is the facility in compliance currently? Have they had issues with compliance? What kind of permit does it hold? Then we need information about the specific emission unit and the specific emission process. We need the emission unit and process IDs. We need the source classification code to tell us something about the unit. We might want to gather design capacity information. And then emission process groups are used in our residual risk program. What is an emission process group? This is where we have aggregated SCCs to look at where the risk is coming from when we do our risk assessment. For instance, within a facility we may have tanks, we may have boilers, we may have fugitive emissions, and we may have specific process emissions. And if we see that the majority of the risk is coming from tanks, then we would want to implement measures to reduce the risk from those tanks. So the emission process groups allows us to analyze the risk results. We need information on control. So we want to know the control measures that are in place. And these could include both physical pieces of equipment, or it might include product substitution. It might include work practice standards. And then for those control measures, we would like to know what the capture and control efficiency is. So how much reduction in emissions do we expect from a specific control measure? Then if we look at the emission release point information, we need the emission release point ID. We need to know the release point type. This is very important in the modeling file. So we want to know if it's a stack release and the type of stack release. It might be a vertical stack, it might be a horizontal stack, it might be a gooseneck stack, or is it a fugitive release? This will determine how it's modeled in the risk assessment. We need to know individual latitudes and longitudes for each release point. We need stack parameters for each individual stack release, and that would include our stack height, our diameter, our exit gas temperature, exit gas velocity, and flow rate. If it is a fugitive release, we need the fugitive parameters. We need the fugitive release height, the length of the release, the width of the release, and the angle of the release. And then finally, we need fence line maps. This is very important so that we can know where population lives around the facility. In some cases, some large industrial sites have bought up a lot of property in order to reduce exposure to population or nearby residents. For the emissions, we need actual emissions. We may want to model the allowable emissions, or what's permitted. We need the pollutant name and the chemical abstract services number for that pollutant. We need operation data. We need to know, when did the emission occur over? Did it occur over the whole year? Is it a peak release over a certain hour or certain days? We also need to know then about the facility. So is it operating one shift 7 days a week, one shift 5 days a week? Is it operating 24 hours a day, 7 days a week? We need to identify how the emissions were estimated. If emission factors are used, then we would like to see the specific emission factor and the throughput data. And then finally, what is the data source? Did it come from the facility? Did it come from an existing inventory? Did the state, local, or tribal agency provide it? Did it come from a regulatory modeling file? So as you can see, quite a bit of information are needed in the modeling files. And as we talked about earlier, on this list of data elements for our quality assurance, we particularly need to look at the emission release point data fields, the latitude, longitude, the stack and fugitive parameters, the fence line maps, and the emission release point type. We need to particularly review the emissions, the amount of the emissions, and the pollutant that we're associating with those emissions from a particular unit and SCC. Does it make sense? Would you expect to see this pollutant? Have you reported the emissions as tons when they're really pounds? You can review the emission estimation methods and information. Now we're going to look at a case study. The facility is a paint manufacturing facility. It produces primers and aerosol paints for plastic surfaces. It is a major source facility, and it is subject to the Miscellaneous Coating Manufacturing MACT regulation, also known as MCM. If we look at a plant diagram, you can see that there are two residential areas close to the facility. There's the Equestrian Heights subdivision, and within this subdivision there is a rest home that is closest to the facility, and there is a trailer park. From looking at this, it would appear that the trailer park is actually closer to our emission release points than the Equestrian Heights subdivision. Let's look now at the facility. So from the plat map, you can see there's an administration building, there's a parking area, and then we have 3 sources of air pollution. There is a production building where they're making the paints, and that is known as OSTAC 1001. So this is a stack release. There are 2 fugitive sources. There's fugitive source 2002, which is next to the loading dock, and that's a grinding operation where they're grinding pigments. You'll also see a second fugitive source, 2001, and that is a tank farm. They have chosen to model the tanks as fugitive sources, but you could model these as point sources. So within the case study, we have the raw material storage tanks in 2001, we had the pigment grinding in 2002, and we had the paint production line 1001. It has a control device, and that's a stack release. The schedule, it operates Monday through Friday, 2 shifts, 7 a.m. to 11 p.m. So we're going to look at our data inputs for the paint manufacturing facility. If we look at the top row going across, we have the facility ID and name, the emission unit ID, so we have 3 emission units, the paint manufacturing unit, the storage tanks, and the pigment grinding units. We have emission process IDs. We have the source classification codes that tell us about the specific unit, the emission release point ID, the emission release point type, the pollutant CAS number and pollutant name, the emissions, and then the stack parameters and the fugitive parameters, and the latitude, longitude of each of the release points. Specifically, if we look at the paint manufacturing unit, you'll see this is a stack release, and we only have 1 pollutant being emitted, the phthalate. And you'll see that we have the stack parameters are filled out, but there are no fugitive parameters. Those are all zeroed out, and we have the individual lat longs. For fugitive releases, you will notice that the stack parameters are included along with the fugitive parameters. For modeling, we retain the stack height, which would be your fugitive height. The stack temperature is retained. For the other stack parameters, the diameter, the velocity, and flow rate, these parameters are always defaulted to the 3 values that you see on the table. So the stack diameter for a fugitive release is 0.003 feet. The velocity of a fugitive release is always defaulted to 0.0003 foot per second, and the flow rate is always defaulted to 0. You'll see for the fugitive parameters that we have the length and the width, and then the angle. So you have the rectangle defined by the length and width, and then the angle rotates it from the latitude, longitude. Mark Morris will show you more about this in his presentation. You will also note that under the pollutants for chromium, we have trivalent and hexavalent chromium. All chromium releases must be speciated into trivalent and hexavalent chrome. Why is this? The hexavalent chrome is the only portion of chrome that has a cancer toxicity. Trivalent chrome has no toxicity, so it is not a carcinogen, it is not a non-carcinogen. So if you collect data for chromium, you must speciate it. The third unit, which are the tanks, it's being modeled as a fugitive, but it's being modeled as a fugitive point. How can we tell this? Because in the fugitive parameters, these are all zeroed out. These data inputs will be used later in the course by Mark Morris when he demonstrates a risk assessment model. Thank you for your time and attention today. If you have any additional questions, please feel free to contact me at my email address.